Okay, hello everyone. Good evening again. So yeah, we're very happy that you're here with us. Now it's our fifth session for this lecture series, and yeah, we're going strong, and we're very excited now, especially for today's lesson. Okay, some session norms. We encourage everyone to engage actively and immerse yourself in this learning experience. Be open and ask away. There will be some new concepts. No, they're not too new, pero yeah, there's still some other new concepts. So if you do have some questions, no, please ask away. There are no dumb questions. And of course, lastly, to respect everyone and let's give each other our undivided attention. Okay. Again, please use the live questions tab on Discord. No, if you have questions and yeah, some updates on our schedule. So we sent this earlier no Monday, and yeah, we'll just remind everyone that our schedule is extended by 30 minutes, no yung lectures natin, just so that we can have better pacing on our lectures. Ayan, sige. And also, yeah, we'll be adding a lab day next week on November 18. No, and then the hackathon would stay the same at November 20. And then the last session, sorry about that. The last session would be on November 25. Okay? All right. The homework is still open for the homework 2. And yeah, you don't no need to upload your collab notebooks for that. And of course, yeah, the- wala namang mga new changes on the homework. Pero yeah, if you still haven't answered it, please refer to the erratum Google Docs na lang. Okay, for homework 3, no, the supplementary notebook will be posted after today's lecture, no, so you can start coding na and start experimenting. And then the homework 3 where you will be answering, no, will be posted tomorrow. So some of the questions from the homework would refer to your supplementary notebook. So you do need to practice and you do need to answer that. Again, no need to upload your collab notebook on the classroom. Pero yeah, you just need to fill up the homework 3 form. That will be posted tomorrow. And then you would have 3 attempts no, to answer the homework 3. So to try another attempt, you can just submit again on the Google form. Response editing is disabled for now. And yeah, if you still want to try to answer even after those first 3 attempts, no, you are free to do so up until you get every item right. No, but only the highest score of those first 3 yung ma-record natin. All right? Okay, so speaking of homework, if you want or if you need help, now we have our homework help channel on Discord, and we also do have some study rooms, yeah, voice channels in there as well. And for the hackathon, ayun, dami nating announcements, right? Pero yeah, for the hackathon participants, no, yeah, reminder that please fill up the official registration form. No, it was sent to your instructors by Ma'am Cherry. No, and yeah, the hackathon mechanics and official invitation letters will be sent on Monday. So yeah, very very exciting. Yeah, yeah, we've been preparing for the hackathon for the past week, and yeah, we're very excited ourselves for that. Okay, last na. For the lab day next week, no, it would be again on November 18. That would be 2.5 hours. No, where we would be really digging into code. No, we'll answer all of your questions about it, the practical parts, no, of our lecture. So we will have lecture today. We will have a glimpse of programming today, no, and then next week we will apply most of the things that will be discussed today. So yeah, as you answer the supplementary notebooks or as you do some exercises, no, if you do have some questions or inquiries, no, you can send them on Discord actually. And then if you want to share them as well on the lab day, that can benefit everyone naman. All right. Okay. And I'll stop rambling about na. So yeah, I'm sure that everyone's excited for the fifth lecture. So we'll be exploring qubits and quantum circuitry. So of course we will have a quick recap on quantum gates, no, and then how can we use those quantum gates, no, those building blocks into quantum circuits, and then yeah, we would have an overview about algorithms, no, special algorithms that we are using in Quant. Okay, so yeah, let's start the first session. No, for quantum circuits. No, I'm happy to introduce to everyone Sir Bobby, the president of One Quantum Philippines. So hello, po, Sir Bob.
Thank you, Jabas. So hi, everyone. I will now share my screen. Are you able to see my slide?
Yes, po, sir.
Right.
Yes.
So thank you very much. So we have prepared a lot for this. Um, the, there was, let me tell you a story. When we were starting Quantum Computing Philippines or One Quantum, so we had this Facebook page, and a friend of mine, he asked me, is it possible for me to start coding in Qiskit without knowing any theory? And I told him, I don't think that's possible, because even if you're even if you're using Qiskit or Microsoft Q Sharp or Google Circ, all of these are using the same concepts. No? So if you don't know them, then it would be hard to create a program that's um, that you can understand. So that's the reason why we first gave you the foundation, so that at this point it's now time for you to uh, be able to start coding now. So when learning quantum computing, it's really the learning curve is really steep, and it's only after you learn the foundations that you can say, okay, I'm now ready to do some coding. Okay. So let me just give a overview of the single qubit operations. This was discussed um, last week by Elmer. So I'm just going to give a very quick overview. Okay. And only those things which I need for this lecture. So last week you discussed about the NOT gate. We symbolize it by X, or by this symbol here, which is a circle with a plus or O plus. So the action of the NOT gate is just to flip the value of the qubit. And for the Z gate, the Z gate will just what it will do is it acts like an identity when you apply it to the zero qubit, but when you apply it to the qubit one with value one, then it will introduce a negative sign, or it's also called a phase change. And this one is the unsung hero of quantum computing. So this is like without this one, you cannot even you won't even have a quantum computing, because Hadamard gate is the one which is responsible for your superposition. Yeah. So what if its action on the zero qubit, it will do a superposition, the usual superposition. But if its action on the one qubit, sorry, there's a typo here. It should be a minus, so 0 minus 1. But when you measure this qubit, the probability of getting a 0 or a 1 is the same, it's 50%. So you can think of the Hadamard gate as your uh quantum coin flip. You flip a coin, give you 50% probability. And this one was also discussed by Ulmer, but we won't get into that today. My plan is to just give you some exercises on rotations. We will cover the basics for this lecture. So, question: if you have two qubits A and B, and you want to keep track of the state, how do you do it? So, we keep track of the state using what is known as a tensor product. So first we need to identify which qubit is, the order in which qubit is first, which qubit is after this qubit. Okay, so for example, for A and B, let's suppose that qubit A is to the left and qubit B is to the right. Then we can write the tensor product of both qubits. This one is a notation. So I'm trying to tell you the different notations that we use for tensor products so that you will not be confused. So this one is a notation. If you see something like this, that's a tensor product of two qubits. You can also write as this one here. So A, and then there is a circle with a multiplication sign, or O times, as they call it in LaTeX. And the third one is you can just concatenate the two symbols inside a cat symbol, okay, AB. So these are all the same, okay? So we can use them interchangeably. So sometimes, most of the time we use this, but when it comes to explaining some mathematics and you want it to be explicit that you're actually using a tensor product, we also use this one here. Okay. So single qubits. So if you have a so we are now familiar with the single qubit operators, right? Like the X gate, the Z gate, Hadamard gate. These are very basic. There are more of them, but we'll just stick first with the basic, because once you're able to understand the basic, it's just so easy to build on top of that foundation. So suppose we have a tensor product, and you have a X gate. Okay, so this single qubit operators, they only operate on single qubits. So you have to specify which qubit you want them to operate on. So for example, if you want to operate the X gate to the first qubit, we will denote it by this one here. So X with a subscript of 0 acting on the tensor product 0, 0, it will flip the first qubit. Okay, now it's quite what you call this, it's quite confusing, because when I say first qubit, I'm actually referring to the qubit with index 0. Okay, so this is the qubit with index 0, and this is the qubit with index 1, but index 0 is the first qubit. Okay, so I hope that will you won't be confused by that. Okay, and then to make X act on the second qubit, we just give it a subscript, X1 acting on this tensor product will give you 1, 0. Okay. Now, usually I will interchange between a tensor product and a state, okay? Because a tensor product is nothing but a state as well. Okay, so this one is the 0, 0 state, okay, which is just a tensor product of two qubits in the state 0 and 0. Okay. Now, if you want to flip the two qubits, then you just do the operation x0, x1 on the on this tensor product, and then it will give you this one here. Okay, so this is basic operator algebra on the tensor product. Now, let's have an example. What gates do you apply to get a 0, 0 into this superposition of state of 0, 0 and 0, 1? Okay, so to do that, first you apply the Hadamard gate to the first qubit. Okay, so you might be asking why the first qubit, because if you take a look at this, okay, if you take a look at this one here is 0 and this one here is 0. Okay, so there's no change, no? But in the first qubit, the 0 became 1. Okay, so you can immediately see, you can immediately think na, oh, probably the Hadamard gate was um, was applied on the first qubit. Okay, so that's what we do, no? So we apply Hadamard to the first qubit. Okay, so what happens here is that take a look at this notation. Okay, so in this notation, what I did was to make explicit that 0 and 0 are actually 0, 0 are actually tensor products. So I put um, a tensor sign, okay, in between them. And also, I applied the Hadamard to the first qubit, and I dropped the subscript, okay, because we know already that it's acting on the first qubit. No, there's no confusion. So that's the reason for this notation. Huh? And then when you apply the Hadamard, okay, then you get this superposition of 0 and 1. Okay, and then finally you bring it back again, right? So you put the 0 back again into this thing here, and then you will see that this is just equal to the problem that you're supposed to solve. Okay, so that's the thing. Okay, so you might be asking, no, so why is it that I'm still doing some mathematics? No, where's the coding? Actually, the coding is so simple, no? And you will realize later that this is like a one-to-one correspondence between the mathematics and the code, no? So even the code, you can convert it to mathematics, no? So that's why I start with this first. Okay, apply Hadamard on multiple qubits, no? So I want to apply the Hadamard on the state 0, 0. Okay, guys, so there's another notation, no? So I just want to tell you all of these notations because in the future, you will be reading quantum computing uh, quantum computing papers, no? And you might be surprised. So what's this, no? Well, this is just the same as this. Okay, so so it's like h, so h, and then raised to the 2 or h squared, but it's actually tensor, no? So h tensor 2. Okay, and then this one here is just, of course, equivalent to this one, h acting on 0. So each Hadamard acting on their assigned qubit. Okay, so this one here, we have this. So h acting on 0, h acting on 0. And then after that, you then substitute the Hadamard expression. So what will happen what is H0 equivalent to, no? So it's just equal to this one. And the same as this one, right? And then after that, you just do a multiplication. Huh? So what happens is this 0 will distribute to this, and then 0 will distribute to this, so you get 0, 0, and 0, 1. And then 1 will distribute to this, and then you get 1, 0, and 1, 1. Okay? So I hope so far so good, no? So madali lang naman yan. And then square root of 2 squared, no? Pero if you think about it, guys, no, this is just a binary number, no? Okay, 0, 0, 0, 1, 1, 0, 1, 1. So if you think of this as binary numbers, you can rewrite this into base 10, and this sum of states now become like this: 0, 1, 2, 3. No? Okay, and since we really like to make things compact, no, we really like to make things compact. Okay, so imagine you're going to write all of 0 to 3. What if it's a 0 to 100, right? So to make it compact, we just do it something like this. Okay, so 1 over square root of this factor here, and then here a summation, x equals 0 to 2 to the 3, no, which is 8 minus 1, or 7. Okay, so oh, sorry, I have a mistake here. Okay, this should be 2 to the 2. Okay, 2 to the 2. 2 to the 2. So it's 4 minus 1. So 0 to 3. Okay. So let's, Javas, if we can take note of that correction, I will check this one. I will modify this. So in general, when you have qubits initialized in the 0 state, for example, n of them, and you want to apply Hadamard to all of them, then this will give us this expression. Okay, so this, guys, you have to take a look and familiarize yourself, because this is the superposition principle, or this is the superposition of qubits. No? This is what makes quantum computing powerful. No? Imagine you only have a few qubits, 10 qubits, or let's say 20 qubits, and then you apply Hadamard to all of those 20 qubits. What will happen? You have a superposition of 1 million, about 1 million states. Okay, because 2 raised to the 20 is about 1 million. Okay, or more than. No? So this is the power of quantum computing. Okay, the power of quantum computing. So that's the superposition. Okay, Hadamard. Whenever you see that, okay, that's quantum computing. Okay, so please remember that. Okay, so I think I forgot to time myself. I only have 30 minutes. Now, quantum computing, quantum computing process, quantum computation process. When we do quantum computation process, okay, so the standard quantum computation process is you have a what is known as the input register. So these are the qubits which are input to your computation, and then you have the output register, which is the output of the computation. And the computation is an operator, no? It's a unitary operator. Okay, so unitary, ibig sabihin yan, it preserves the inner product, or the length of the vector. So ito yung ating this one is the input register, and this one is the output register, and this one is your function, okay, or f. So if you see this one, then it actually means the input register stays the same, but the output register will change by doing a XOR, exclusive OR, to the number y. Okay? And the number given by f of x. No? So ano ba ibig sabihin ng exclusive OR? So yan, ito yung ibig sabihin. No? So for example, if your number x is 1101 and your f of x is 0111, then the exclusive OR is like this, no? It's like addition by 2, addition modulo 2, no? So 1 plus 1 will give you 2, okay? Modulo 2, 0. Or kapag, so 1 and 1, so 1 or 1, x or pala, 1 x or 1 is 0. 0 x or 1 is 1. So basta magkaiba yung kanilang magkaiba yung kanilang digits, ano yan, ibig sabihin 1 yan, no? Pero kapag pareho, like puro 1 or puro 0, then it's 0, no? So 1 or 1, 1. Itong dalawang 1 will give you 0, okay? Now, this is an exercise now for you to think about, no? If I have a number like any number z, which is expressed in binary, if I get the XOR of that digit, then it will give me 0. Okay? So, it should be easy, no? Kasi pare-pareho lang naman sila eh. So, you have a number, z, expressed in binary, and then you XOR it with itself, no? It turns out that the answer is 0. Okay. So, itong quantum computing process is called reversible computing, no? Kasi ito kasing ating unitary operator called UF, it is its own inverse, no? That's the good thing about the unitary operator, no? It is its own inverse, no? So if you so ito ibig sabihin, no? So if you multiply UF by its inverse, then it will give you the identity. So therefore, to show that yung computation is actually reversible, what we can do is we do this, no? Ito yung quantum computing process, no? We define this already, no? And then we want to reverse that, no? I-reverse natin yan. So mangyari is that yung quantum computing process is defined to be like this, no? X pareho, pero Y X or sa f of x. Okay? Pagkatapos, so since this one, since UF is its own inverse now, ibig sabihin UF of -1 is equal to U of F. So we are actually just applying again for the second time the quantum computing process, no? So ibig sabihin pareho pa rin yung X, pero ito, which is this one here, i-XOR na natin sa f of x, no? Pero di ba sabi natin kanina that a number XORed with itself will give you 0. So therefore, this one will just equal to XY. So reversible process siya, no? And that's that's one of the highlights, no, of quantum computing, no? Kasi it is energy efficient. Yung classical computing kasi maraming mga operations dyan that are non-reversible, no? So kapag hindi kasi reversible, it will generate heat, no? And if it will generate heat, then heat dissipates into the environment, which makes the process inefficient, no? So hindi siya energy efficient. Okay, now that we're done with all of those intro, let's now go into Qiskit. Jabez, may okay pa ba? I can still continue now?
Yes, po. Please continue.
Okay. So, guys, what is a quantum circuit? No? I have been talking for about 30 minutes already. And ngayon ko lang introduce yung quantum circuit. Pero, pero I did not tell you that all of those things that I was already discussing, they're already the circuit, no? Those are already the circuit. Pero gusto kasi natin i-program siya, no? We want to put it in a visualized manner, no? And we want to be able to do some coding, no? So let's define the so ito yung quantum circuit from a programming perspective. So kanina we were talking about qubits, di ba? Mga qubits na yon, these are the tensor products, no? So ito na yung mga qubits na yon, no? This is the first qubit, second, third, and third qubit, no? Tapos yung qubit natin, meron yang input and input register at meron ding qubit na output register, no? So ito yung input register at ito yung output register. Now, since we want to be able to get an answer, we need to be able to measure, no? Now, when we measure a quantum system, we have to record the result of the measurement somewhere, no? So this is where the classical bits come in, no? So when you measure, ito yung ano, this is the what you call this? This is the icon of measurement, no? So for example, this one here goes to lahat sila goes into the classical bits, no? Yan ang tinatawag na measurement. And then itong quantum gates, no? So ito yung mga X, mga H, no? And this one, I think na-discuss na to ni Elmer, eh. Is the control knot, no? I'm sure na-discuss na niya, no? And this one is the again the Hadamard, no? Now, what's so special about this circuit? Bakit ito yung nilagay ko dyan, no? This circuit is actually an implementation of what is known as the Deutsch-Joshua algorithm, no? Which our friend Lance is going to tell us more about next week, no? So, ang maganda kasi sa Deutsch-Joshua algorithm, doon mo ma-realize na iba pala talaga yung pag-iisip ng quantum computing, no? This is ibang klase, no? Yung how you use probabilities, no, in order to get the answer, no? This is really a very nice problem. Okay, now when we program, we usually have imports, no? Tapos those imports are usually just the same, no? So we just copy paste them and put them in our editor, no? And there's one function, very important function, which allows us to simulate, no? So itong simulate, since we are not going to use the real quantum computing hardware, no? Kasi na-mention nga ni Burns last time na it would probably take weeks, no? 2 weeks before you get an answer. But that's good if you have very large problems, no? Pero for problems that are minimal number of qubits lang, no? Okay na yung simulator, no? Unless, of course, possibly kapag you want to simulate 50 qubits, that's hindi na pwede yan, no? Because you need 1 petabyte of memory, no? So hindi pwede yung 50 qubits, no? So, pero for example, 5 qubits, no? Okay yan, no? So we use a simulator. And the reason why okay lang yung simulator is because your quantum algorithm will behave the same whether you have 5 qubits, no? Or more of these qubits, no? Okay, so here we just use a simulator, and then we plot the result of the simulation using histogram, no? And shots is the number of times we do the computation, no? So sa quantum computing kasi, it's all about probabilities, no? And then probability, ibig sabihin yan, you need to gather statistics, no? You need to repeat your experiment in order to get what is known as the expectation value, no? Or the average, no? Kasi yung average, yun yung ano mo, yun yung sagot ng computation mo, no? So this one, you just copy paste that, no? And put it into your Jupyter notebook. Okay, so let's do something like this now. So ginawa ko, I just pasted the simulate, no? This one here. Klaro pa ba, Jabez? Is my screen still readable?
Yes po, sir. Maybe you can actually make the PPT smaller and the code, the IBM Quantum, bigger po.
Okay, sige. Okay, let's make this smaller. And okay, gawin natin ganyan.
Yes, po. There you go.
Okay, so copy paste, no? And then we just run that, no? Okay, na-run ko na ba? Okay, so, and this one here is the code, no? Now, okay, our first experiment, no? How do I make a qubit, a 1 qubit, no? A qubit in the state 1. How do I make a qubit in the state 1? Kasi normally, a qubit is in the state 0, no? Ground state. So it makes sense na kasi imagine if all your qubits are initially in the state 1, that's an excited state, no? So ibig sabihin it needs energy, no? So dun muna tayo sa ground state, no? Ground state, which is state 0. Now, how do I make that into a state 1? So simple, no? Ang gagawin natin is we just flip the qubit, no? So ito 'yon, no? Ito ginawa natin yan, x. So gawin natin x yan, no? And then we run it. And then we get this nice drawing, no? So ito yung ating quantum circuit, no? Okay. Now, how do I know na okay, but how do I know na naging ano na to, na naging 0 na yan, no? Oh. Okay. Let me just restart, no? Sorry for that. Where is it? Okay. Titled view. Okay. So because it restarted, I have to repeat this. Okay. And then we just do a simulation. Huh? So let me, okay. I just want to, so simulate it, no? So makikita natin that whenever we repeat the experiment 1,000 times, no? The output should always be 1, no? State 1. Okay, no? State 1. Now, kapag tanggalin natin yan, no? For example, I'm gonna remove this. Sorry. I'm gonna remove this. So, ang mangyari, no? Nawala, no? So, if I simulate it, I should be in the state 0. Okay? So, yun. So, that's so, kung nakikita mo, almost everything that we will do in the programming, lahat to mga boilerplate lang, no? Lahat yan. We don't need to change that, no? dito lang tayo nag-change. Dito banda, no? Dito lang tayo nag-change. No? Yan. So, yan. This is where we change, no? Yan. To create our circuit. So later we are going to create more complex circuits. Okay, so I was wondering, no? So ano ba talaga yung when you are a programmer kasi you want to minsan you want to know what's the hello world, no, of programming, no? In C it's a hello world, no? But in in quantum programming, what's a good hello world, no? Kanina I started with X, no? That could be a hello world, no? Pero this one is actually much better hello world because this one is actually using a quantum uh, phenomena na nakikita mo talaga, no? This is called the superposition, no? So this is the Hadamard gate, no? QC.H. So if you run that, it will give you this one H, no? Now, if you simulate this, alam natin, di ba, na the Hadamard will be 50% 0, 50% 1, no? So if we gather the statistics, no, more or less pareho yung distribution nila, no? So let's do a simulate. Okay, so as you can see, the state of your qubit is nahati, no, between 0 and 1, and yung pagkakahati niya, this is the number of times, no, that it occurred. So 498, 502 is more or less the same. But theoretically, it's the same. Okay. Okay. So, balik tayo, no? So, ito yung Hadamard, no? So, alam natin that Hadamard is gonna be put your 0 into superposition, and ito yung kanyang result, no? Okay, exercise time, no? Create a circuit that transforms the following, no? I have a 0 qubit, and it will transform it into this one here. So, guys, no, especially, no, if you are if you are participating in the hackathon, no? So please pay attention. This is the meat of the hackathon, no? So it will be about questions like this, no? How do you create something like this, no? So pay attention, and this is also the meat of our lecture series, no? So if you get anything out of it, no, it's actually we want you to be able to write circuits, create circuits after this lecture series, no? And yung mga algorithms na yan, which will be given by Jeff, no? Yung foundation of those, no, is this circuits, no? Now, let's go back to our exercise, no? How do I make a 0 qubit into something like this, no? Okay, that's a really nice question. Okay, answer. Una, maybe hindi pa nyo familiar, no? But I need you to familiarize the action of the Hadamard on the 0 and the 1 qubit, no? Kasi the action of the Hadamard on the 0 qubit is this one here, exact plus yan. Pero if you apply the Hadamard on the qubit in the 1 state, ito yun minus. Okay? So anong ibig sabihin niya, no? Galing dito, how can I go into this one here? So what you'll do is first flip this into 1 and then apply the Hadamard. So ganun siya. Okay. Now, as I mentioned earlier, no, it's so easy to program. So I just put it here. It's an easy exercise to convert this into a circuit. No? So how do we make this into a circuit? Let's go back here. No? Okay, just do something like this. No? QC x of 0. So itong 0 na to, this is the index of the qubit. No? We only have one qubit. No? Take a look. No? We defined a quantum register of 1 qubit, and we defined a classical register of 1 qubit. Okay? Tapos, we created a circuit out of this quantum register and the classical register. So we have this one here. So if we run this, ito na yan. No? Okay. Now, I don't need to simulate this kasi alam naman natin na the Hadamard always in superposition, pareho lang yung probability, no? But if you're really curious, no? 0, 1. Now guys, no? The thing na hindi nyo nakikita dito is yung negative sign, no? Negative sign ng Hadamard when applied to the 1 qubit, no? Paano natin makikita yan? So punta tayo dito sa composer. Okay guys, no? So probably I went ahead of myself now. Hindi ko man lang sinabi na this is the IBM composer pala, no? So this one and this one here, this is the Jupyter notebook of IBM Quantum, no? And in the same UI, you can also get the composer. Itong mga composer na to will allow you to to visualize things na hindi na visualize dito, no? Well, you can actually visualize, but if you have to program, no? Which which is mas easier kasi ito, no? So let me take a look at this one here. Okay, Hadamard. Okay, so take a look. Okay, let me remove that first. Okay, now if I put an X, ito yung X, no? This one is the so what happens is yung state niya is now 0, 0. Just pay attention to this first qubit here, no? Kasi yung the way they design this composers, that this is composed of four qubits, no? So 1, 2, 3, 4. So, but we are only interested in the first qubit. Now, I mentioned earlier na hindi natin nakikita yung pagka-negative or the phase, no? The phase difference between the 0 qubit and the the phase difference between when you apply Hadamard on the 0 qubit and the one with the 1 qubit, no? Kasi when you apply it in 1, merong negative sign, no? Sa 0. So titingnan natin yun ngayon. This is where you pay attention, no? This one here. I'm not sure if it's clear, no? Pero let me just adjust it, no? So ito, pay attention to this one, no? So if I put so this one is now in the 1 state, no? If I put a Hadamard here, oh, take a look, no? Nag-iba, no? So ibig sabihin yan, nagkaroon siya ng phase difference of pi, no? Yan. Okay. Okay, let's go back to our lecture here. Okay. Now, another exercise, no? Create the circuit that does the Fourier transformation. Okay, take a look, guys, no? This is, pag nakita nyo kaagad dyan, no? Immediately, you'll recognize that's the Hadamard, no? So dapat zero, dapat this arrow, no? This one is an arrow. So, sabi dito, recall that when you have this qubits here initialized to 0, all of them, 3 qubits, and then you have apply a Hadamard to all of them, ito yung magiging itsura niya, no? So, ibig sabihin, all of the qubits, you put a Hadamard gate, no? So, ito yung ginagawa niya, HHH, no? So, ganun siya. So, this is the answer to this question. So, HHH. So, dito, hindi, dito sa diagram na to, hindi halata, no? Pero, hindi halata yung mathematics. Ano nangyayari sa nakikita nyo lang, okay, H in, meron kang H dito, may H ka dito, may H ka dito. Pero actually, ito talaga yung itsura niya, no? This is just a this is a summation of states from 0 up to 7, no? So 2 to the 3, 8 minus 1, 7. Okay, tapos dito, this one is meant to confuse you, no? So I equals 0, 0. This is just binary of 0, and this is binary of 7. Okay, another exercise, no? Create the circuit for the following transformation. So you might be wondering, why do we need to create all of these circuits? And the reason for that is you cannot do quantum computing if you don't know how to create circuits, no? and and that's the reason why it's a very essential skill, no? To be able to, pag nakita mo yan, how do you create a circuit like that, no? How do you create this kind of mathematical uh, this kind of state, no? In using the circuit diagram, no? So do that. Okay. So ang gagawin mo lang is you realize that sorry guys. Okay. Okay, this one here nasobrahan lang ako ng type, no? Wala yan. Okay, wala yan. So actually you just itong dalawang na to, and then if you multiply them, no, it will give you this one. So ito yung this is the problem, no, which we are trying to solve, no? So it turns out na you only need to put 2H, no? H dito at H dito. So if you get this mathematical symbols, no? Or yeah, if you get that mathematical symbol, you can translate that easily into a quantum circuit, no? So for example here, H punta dito, H punta dyan, no? So itong circuit na to will give you this. Okay? Will give you that. Next. Ayun. Create the circuit for the following transformation, no? Galing sa 0, nagkaroon tayo ng ganito, dalawang state, no? Pero, it's a superposition. Pero nakikita nyo na dito, 001, and dito 101, no? Now, how are we going to create a circuit that will give us this vector or state vector, no? So, ito lang yun, no? We begin by noticing na itong form na to, no? Yung forma na yan, Hadamard yan, no? So, one of the qubits must have been applied a Hadamard gate. Pero hindi natin alam saan, no? Ano ba yung in-apply? Where should we apply the Hadamard? No? Will it be in the first, second, or third qubit, no? Pero alam natin Hadamard yan, no? Okay. Pagkatapos, ito kasi yung problem, no? So, hinadamard natin. Pagkatapos, okay, makikita nyo dito na itong zero, itong third qubit, no? By the way, we count qubits from the right, no? So 0, 1, 2. Okay. So itong third qubit from 0 naging 1, no? So most probably the third qubit is the one na may Hadamard, no? So pagkatapos, so let us say we apply the third Hadamard to the third qubit. What will happen? Ito yung mag-itsura niya, no? From 0 to 0 to 0, 0 to okay. Then apply the X gate to the third qubit. It will give the result, no? So apply X gate to the third qubit.
It's now time to drink water.
Okay. Zero, 1, apply X gate to the third qubit. This will give you okay, let me get back to that, okay? Nagkamali ako ng type and then ngayon mas nalito ako. Okay. But don't worry, no? I will correct this and we're going to discuss this next week, no? Okay, punta tayo sa Z-gate transformation. So Z-gate is yung Z-gate when applied to the 0 qubit, it will just be the identity, no? So 0 just becomes 0. Pero when you apply it to the qubit na 1, it will introduce a negative sign, no? Or there's a phase factor that was introduced. Now, so very simple, no? Very simple. Ngayon, to code it, ito lang yung ano niya, Z of 0, no? Z of 0. Okay. So let's do that. Let's go back here. Okay, so let's go back here and let's introduce a so QC that Z of the first qubit. So ito lang yung itsura niya, no? Ito lang yung itsura niya. Pagkatapos, but this one here will give you the kasi initially kasi yung state ng qubit is 0, so this will give you the 0 state pa rin, no? So now if you apply this to para so that we can apply it to the state 1, you have to flip first the first qubit before you apply the Z gate, no? Now, hindi at the again, hindi obvious yung negative sign, no? So, balik tayo dito. So, negative sign, no? Ito yun. Open natin tong Z gate na to. So, tanggalin lang natin yan, no? Okay. Now, pag maglagay tayo ng Z gate, which is this one here. O, tingnan nyo, no? Okay. Z gate. Pareho lang, no? Walang change, no? Walang change. And the probability is the state is still in 100%, nasa state 0 pa rin siya. Pero ngayon, pag nilagay natin ginawa natin pinlip natin yung qubit before we apply the Z gate, like this. So naging 1 na siya. So the probability, nasa state 1 na siya ngayon. Tapos ito, bumaliktad, no? So kung titingnan nyo, itong line na to, magkaiba dito, no? So it's like it rotated 180 degrees, no? Pi. So that's the Z gate. Okay. So example, no? So we know that the Hadamard acting on 1 will give you this superposition, no? Na may negative. How do you achieve galing 0 papunta dito, no? So galing 0 papunta dito. How do you do that, no? So using only the Z gate and the H and the Hadamard, no? So first, gawin mo munang i-apply mo muna yung Hadamard. You apply Hadamard to the 0 qubit to give you a superposition, no? And then you apply the Z gate, no? Kasi Z acting on 0 will give you 0. Okay, Z acting on 0 will give you 0. But Z acting on 1 will give you negative 1. Kaya, ito siya, no? That's the answer, no? So now, we now move on to the control X gate. Okay, I think I will have to extend pa, no? Kasi medyo madami pa to, pero probably another 30 minutes or 25. So the control X gate is the one which will affect the logic, the Boolean logic called XOR, no? So so ito yun, no? So you have 2 qubits, A and B. Now, if you apply the control X, what will happen is that A will still stay the same, and B will be, the value of B will become B XOR A. No? So I hope you still remember that this one is the standard quantum computing process now. So standard quantum computing process, the input is still there, not changed, only the output has changed. No? So this is a reversible process. So to program the XOR or the control NOT gate, you have to identify first the control qubit and the target qubit, no? So yung control qubit will determine, no, whether the target qubit will be flipped, no? Kasi alam naman natin na kapag NOT, no, or X, pag sinabi natin NOT, it flips the value, no? So NOT of 0 is 1, NOT of 1 is 0, no? So when I say the control qubit will determine whether the target qubit will be flipped, yan ibig sabihin niya, no? It will apply the NOT gate to the target qubit. So yung control qubit mo dito is the one with a circle, no? Small circle. And then here, the target qubit is the big circle with a plus sign, no? Or the XOR sign. Okay. Okay. So let's let us do that, no? Tanggalin natin. Okay. First, what will happen if we have ito yung control qubit, okay? And ito yung target qubit. Now, kapag 0 yung control, it will not do anything to the target, no? It will not do anything. Initially kasi lahat yan puro 0. So 0 yan, 0 yan. So the effect of the control NOT on the 0, 0 state is identity lang, no? Nothing will happen. However, if we make the first qubit into a state 1, what will happen to the target qubit, no? Tingnan natin. How do you do that? Okay, take a look, no? So, naging 1, 1 na siya, no? Kasi ito naging 1, and ito naging 1 na rin, no? So, if you take a look, the state is in 1, 1. Okay? Now, what happens if this one is also in state 1? What will happen, no? What if this one, if the target qubit is also initially in state 1, what will be the result? Yan, bumalik siya dito, no? Kasi, because this one is state 1, and this one is state 1, itong control qubit na to was triggered, no? And kasi state 1 siya, ni-flip mo siya, no? So, from 1 naging 0. So, kaya, ito na yung state niya. Okay? Now, however, kapag 0 yung control qubit mo, initially 0, what will happen? No? What will happen to the state 1? Okay? Will there be an effect? Okay, yung state 1 yung state 1 bumalik sa qubit state na 1. Okay, so ito yung so yung nakikita nyo, pinaka right side na 0 is the first qubit, and yung katabi niyan na 1, it's the second qubit. So this is the control knot. Okay. So very easy din to to program, no? So we go here and we just do this, no? So first we have to make 2 qubits, no? Okay, don't forget, okay? Tapos we just apply Cx, no, to the yung control qubit natin, let us say, is the first qubit, and target qubit natin is the second qubit. So ito yung itsura niya, no? Yan, ganyan yung itsura niya. Okay. Okay. Great. Only 20 minutes. Now, next problem. Create a circuit for this one here. So we have 0, 0, naging 0, 0, and 1, 1, no? So, ibig sabihin, one of these must have been given a Hadamard, no? So, tingnan natin saan yung nag-Hadamard dito. So, ito, posible kasi na ito, ang first qubit, binigyan mo Hadamard, pwede rin na yung second qubit, binigyan mo ng Hadamard. No? So let us say, if we apply the Hadamard to the first qubit, ito yung mangyayari, no? Sorry, so we apply the Hadamard. Actually, pareho yung no, whether you apply it on the first or the second qubit. Dito pala sa aking equation, I applied it on the so this is where it gets confusing, no? Kasi the first qubit is usually the 0 index, no? Not the index with 1. Pero dito, you apply H1, so to this qubit, no? Itong qubit na yan. So this will become 0 and 1. Okay? Tapos itong qubit na to will remain 0. Pagkatapos, you apply a control knot, no? Control knot to the with the second qubit as the control, no? So kapag mag-apply tayo ng control knot with the second qubit as the control, ang mangyayari dyan is titingnan mo ngayon ito. 1 ba yan? Or 0? Kung 1 yan, gawin mo tong i-flip mo to. However, 0 kasi siya eh. So, ibig sabihin, walang nangyari. Now, 1 ba yan? Yes. So, since 1 yan, then we have to flip this. So, ito yung nangyari. No? So, ganun yung itsura ng circuit. No? Okay. So, pareho din to, no? Pag in-apply mo dito, pag yung H nilagay mo dito at yung control nilagay mo dito at itong plus nilagay mo, pareho lang yung ano niya, mathematically, no? It's still the same. Okay, Toffoli gate. So itong Toffoli gate, ito yung tinatawag na AND gate, no? Kasi may dalawa kang qubit and you check whether those two qubits are in the one state. Kapag nasa one state sila, uh, the Toffoli gate will then initiate a flip on the third qubit. So Toffoli gate is the first 3 qubit operator that we have encountered. Okay, so Toffoli gate is a 3 qubit operator, no? Yung control X is a 2 qubit operator. Ito naman 3 qubit, no? It needs 2 control bits and 1 target bit, no? Ito yung control bit. Ito may small circle, to big circle dito. Ito yung the target qubit. Okay. And napakasimple lang din yan, no? So CCX lang, no? Control X. So let's do that here, no? So I have to make this into 3, okay? And convert this into CCX. So 0, 1, tapos yung 2 yung ating target, no? So ito may itsura niya. Oh, sandali lang. Yung itsura niya, yan. No? Control, or Toffoli gate, no? Control X. Okay. Okay, napakasimple, no? Now, punta na tayo sa mga problems. How do you implement a NAND gate? Okay, using a Toffoli gate. So may dalawa kang qubits, represent it as A and B, no? Or ito na lang, ito yung dalawang qubits, first and second qubit, no? Tapos meron kang third qubit, which is the target, no? Alam natin na this one is the AND gate, di ba? So in order for this to become an AND gate, you just put an X here, okay? So you just flip, okay? So ito na yung this is the result of A NAND B, no? Okay, this is really good, no? Guys, how do you implement an OR gate, no? So you might be asking, no? Wow, puro na to logic, ah. So, and the reason for that is computing is all about logic, no? So if you remember, when you add 2 numbers, no? When you have a calculator, meron tayong tinatawag na binary adder, no? In fact, you can create a binary adder as a circuit, no? And that would be a very good challenge. Pero dito, lahat naman kasi ng computing natin is all about manipulation of bits, no? So we have to know how to do this kind of things, no? Like implementing an OR gate, not an OR gate, but an OR functionality, no? Logic. So simple lang, no? Una, we have to create a truth table, no? Ito yung tinatawag na truth table. And then we enumerate all possible values of A and B, no? All combinations. And then we get the result, no? So yung OR kasi, if A or B merong 1, then the result is 1. Kapag puro sila 0, that's the only time that it's 0, no? So, nakikita mo, may 1 dito, 1. Merong 1 dito, 1. Silang dalawa, 1. Okay, 1 yan. Basta, kapag may isang 1, 1 na yan kaagad, no? So, isa, dalawa. Now, how do you implement this? Now, itong 1 and 1, we can implement that using the Toffoli gate, no? Control, Control, X. Pero how do you implement this one here? 0, 1, 1, 1, 0, 1. So, ito na yon, no? Kapag nag-1 to, so gagamitan na natin ng Control X. Pag nag-1 to, gawin mo tong flip mo. I-flip mo yung ano nito. I-flip mo yung value, no? So, ito din, i-flip mo yung value. So, initially kasi 0 yan, di ba? So, kapag puro sila, let us check, no? Let us check. Tama ba talaga, no? Initially, 0 yung 0 itong qubit na to. Now, kapag 1 yung A, yung 0 naging 1. Pag 1 yung B, yung 1 naging 0. Pero, because 1, 1 silang dalawa, this one will come to the rescue, no? Since 1 and 1 to, itong 0 dito, naging 1 na ulit. No? So, you can actually check for the correctness, no? Yeah, you just base it on the truth table. So this is how you program it, no? And it's so easy to program that in Python. So CX, may dalawa kang CX at may isa kang CCX, no? So let's do that, no? So ganun lang siya, no? So QC CX from 0 to 2, okay? Then QC that CX from 1 to 2, okay? And then CCX 0, 1, 2. Okay? Yan. Simple, ha? So kaya, minsan, since very simple yung pag-program niya, doon tayo sa mas mahirap, which is ito, no? Ito, this is the mahirap part ng quantum computing. It's actually understanding or coming up with the mathematics. Kasi once na kuha mo na yung math, napakadali, no? I-convert into a circuit. When you see a circuit, you can immediately see the mathematics. So puro math yan. Okay, create a circuit that will result in the following transformation. So yung 0, 0 mo will become like this, no? Now, tingnan nyo, no? Naging 4 siya. Ibig sabihin, may dalawang qubit dyan na nilagyan ng dalawang H. So, may dalawang qubit dyan nilagyan ng H, no? So, Hadamard. Pagkatapos, ginamitan to ng control X, no? Kasi, so, basahin na lang natin, no? The solution is like this. No? Apply Hadamard gate to the first and second qubit. So, itong dalawang qubit na to, i-apply the Hadamard, no? So, mangyari is this one becomes 0, 0, 0, 1, 1, 0, 1, 1. Okay? That's the Hadamard. So, ano yung hindi nagbago? Ito, 0. Ito, 0. So, the third qubit, 0 lang palagi. So, ibig sabihin, yung first and second qubit, yung nagbago, no? So, hinadabard natin yung dalawang first and second qubit, tapos ito yung nangyari. Naging superposition of 4 states. Now, sabi dito, let's focus our attention on this one here. Okay. Sorry, ito pala. To convert this to 110, we apply an X gate to the first qubit. So, gawin natin X ang first qubit, no? So magiging so if you apply an x gate to the first qubit, ito lahat, ito yung magiging itsura niya, no? Apply a x gate to the first qubit. So ano yung first qubit? Ito yung pinaka right side, no? Okay, pinaka right side. So magsimula tayo dito. 0 going 1. 1 going 0. 0 going 1. 1 going 0. Now, compare this one here. Okay, nakalimutan ko lang yung square root of 4, no? So, may 1 over square root of 4 pa to. Pero kung titignan nyo, this one here is the same, no? 0, 0, andito. 0, 0, 1, andito. 0, 1, 1, andito. At, saan yung 1, 1, 0? Convert this into 1, 1, 0. Oh, sandali lang. May kulang yata ako dito, ah. Okay, kulang pa pala. Kasi after that, you have to apply the control not gate, no? So yung control mo is 0 and 1. Control mo is 0 and 1 and yung target mo is 2. So anong ibig sabihin nito? Kung titingnan mo to, kasi gusto nating makakuha ng ganito eh. Gusto nating makakuha ng ganito, no? Paano natin kukunin yan, no? So kailangan maghanap tayo ng may 1, 1. Tapos, apply natin control X, no? So, kapag in-apply natin yung control X, ito yung magiging itsura niya, no? So, itong 0, 1, ito kasing 0, 1, ito yung control qubits, no? Now, this will not have any effect kasi dapat 1 lahat, no? So, this one will stay the same. This one will definitely stay the same. This one will become 1, 1, 1. And this one will stay the same. Okay? So, ibig sabihin, after applying the control not, ito yung naging itsura niya. Lastly, we have to apply the X gate, yung pinaka-last, no? Kasi gusto nating maging 0 siya, no? So, pag maging 0, kung gusto nating maging 0 siya, apply natin X gate. So, this one will become we apply reverse the X, no? So X of 0. So apply X on the first qubit. This becomes 0. On the ito, naging 1. Ito, naging 0. Ito, naging 1, no? Okay, so ito yung kanyang implementation, no? And as you can see, itong series of transformation na to, this is the mathematics, no? So the mathematics, you convert it to a circuit. It's so easy, no? And this one, it's so easy to convert into a circuit also. May dalawa kang H, no? Hindi ko pala nalagay H dito. Okay. Pero the important thing to understand here is that it is very important to know this kasi this one is just a direct translation. Okay. Actually, I still have lots of things in the slide, no? Oh, sorry, hindi pa pala lots pala, but I still have 1, 2, 3 more, 4 more slides, no? Pero okay lang because next week we are going to have a the entire 2.5 hours, no, dedicated to this, no, because this is very important. And this week then, I'm going to give you a lot of exercises, no? So that you can try on your own, no? So these exercises, um, ano siya, mostly pencil and paper, no? Mostly pencil and paper. Kasi ang dali lang i-program. Dali lang i-program. It is the pencil and paper that's very important kasi yan yung algorithm, no? Once you have your algorithm, the programming is so simple na. Okay? So I guess dyan muna ako, Jabez, no? I'll turn over muna to Jeff so that he can talk about the algorithms.
Awesome. All right. Thank you for Sir Bob on that very comprehensive actually review of the gates and then application into IBM Quantum in Qiskit. So yeah, guys, yeah, probably still up in the head. Nandito pa lahat since we still haven't done it on the code yet, no? Pero yeah, we will give a lot of exercises throughout the week so that you can try them by yourselves, no? And also, as Sir Bob mentioned, no, if you do have some questions, the Discord will be open and we will try to
Yeah.
reply as soon as possible. And yeah, and of course the lab day on that day on next Saturday. All right. So at this point, now before moving forward to Sir Jeff's talk, now let's have a well-deserved 10-minute break, just so that we can settle in muna and before talking or before listening in na kung ano ba yung mga applications like the higher level into algorithms. Okay. All right. All goods. All goods. Okay. Now start it. Okay. See you in 10 minutes. Have a nice rest. Hey, hello, hello. Welcome back, everyone. And we hope that you had a nice rest. Okay. Yeah, and without further ado, no, we want to maximize the time. No, so hopefully, the things that were mentioned that were discussed by Sir Bob earlier, no, nagsettle na sila. And now we'll discuss a bit more high level, no, about the algorithms and the techniques, no, that actually very, I would say genius mathematicians and quantum physicists were able to develop, no, and yeah, some of these are the basis, no, kung bakit we do quantum computing because of the speed ups that we can do, the speed ups, the efficiency gains that we can get using these algorithms. So yeah, without further ado, I would like to introduce Sir Jeff. No, he is the supervising science research specialist at the OST ASTI and our very special speaker for the night about quantum computing algorithms. Hello po, Sir Jeff.
Hi, good evening. Am I coming clear?
Yes po. Clear.
Okay, so let me share my presentation. Okay, is my screen visible right now?
Yes po, sir.
Okay. So until what time can I present, JBS?
You can until 7:25 po.
Okay. Okay, so let me try my best to cover everything I prepared. Um, so good evening and thank you to Sir Bob for discussing the um, concepts on quantum gates, quantum circuits, and a brief overview on the programming component of quantum computing. So, in this session, I'll be presenting about some seminal quantum algorithms that were discovered. I think most likely these are in the late 80s or um, early 90s. Okay, so these are textbook algorithms, but and they are, I would say, a lot simpler than compared to the current more complex quantum algorithms that we have right now. But these algorithms um, showcase what quantum computing can do for us. So magagamit dito yung mga na-mention ni Sir Bob kanina na mga concepts. And I hope makita natin kung paano pinagtatahi-tahi yung mga operations or gates na na-mention ni Sir Bob kanina when designing a quantum algorithm. Okay, so again, I am Jeff, and I am from the Advanced Science Technology Institute of the UST, and I am a researcher. I do research work on AI and quantum computing. So let me start. So for the learning objectives for this session, we have three. So first is to identify and explain um, in high level the inner workings of some early quantum algorithms. Second is to explain how these early quantum algorithms are advantages over their counterpart classical algorithms. And lastly is to identify and explain key subroutines in these early quantum algorithms. Okay, so let me use a laser pointer. Okay. Now for the lessons in this session, so first we'll be going through just a brief review on circuits and circuit complexity, followed by circuits and query complexity. Third would be on quantum oracles. Fourth would be on quantum phase oracles. Fifth would be the early quantum algorithms, and we'll have a very brief summary of what has been presented. Okay, so first, let us talk a bit about circuits and circuit complexity. So we can define circuit complexity as the least number of gates used in implementing a quantum algorithm. So um, this is with respect to a universal set of quantum gates used in the target hardware. No, so different physical implementations of quantum processors uh, utilize different universal set of quantum gates. So when we say universal set of quantum gates, these are quantum gates that we can use for general computation. Okay, and this type of complexity, circuit complexity, is a bit difficult to determine because it is not easy to identify whether the current set of gates that we have for implementing a specific algorithm is already the least number of quantum gates that is necessary, okay, to make the circuit effective in implementing a quantum algorithm. Um, and we say that a quantum algorithm is efficient um, on a particular hardware a if its circuit complexity is in polynomial with respect to the number of input qubits. So when we say polynomial, as n grows, n, which is the number of qubits uh, in the circuit, the number of gates grows in a polynomial manner. Okay? So we don't like circuits na nag-grow yung number ng gates exponentially kasi that will require a lot of energy. So gusto natin, maliit lang yung number ng gates that implements our algorithm. And we say that these algorithms are implemented efficiently on these circuits if polynomial lang yung growth ng number of gates with respect to the number of qubits. Okay, so here we have a decomposition of the Toffoli gate. Okay, so we have several 1 qubit and 2 qubit gates in this decomposition. So to implement a Toffoli gate in this particular set of universal gates, um, we need this particular quantum gates. Okay, so I think some of these have already been discussed by Sir Bob, like yung Hadamard gate, control NOT gate, or control X gate na mention na kanina. Okay, so it doesn't mean that when we write a circuit, when we design a circuit, like for example yung Toffoli gate, automatically may native implementation yan sa hardware. So at times, kailangan siyang i-decompose into the set of gates na implemented doon sa hardware. Okay. Just to mention, I have just two references for this presentation, and you can look it up later. So I have added some citations so you can be well guided. Okay, next. Now, that is circuit complexity, and now we have what is so-called query complexity. So this can be used as a replacement for circuit complexity as metric for measuring the efficiency of quantum algorithms or its implementation in circuits. So what is circuit complexity? So we can define circuit or query complexity. So we can define query complexity um, in a quantum circuit by the number of calls of the algorithm to a so-called black box function. Number of calls or number of queries to this function, which we may also call an oracle, no? So sa nomenclature sa quantum computing, they use the term oracle since it is a black box operator. We don't really mind, no, kung paano ini-implement itong operator na to. What matters is that when we give an input to this oracle, it answers us back, and we assume that the answer is correct. So why is that so? Because we are not really concerned about the we're not really concerned about the number of gates of these circuits, but instead we are concerned with the number of queries that is made by the algorithm to this oracle. And these problems that are solved using so-called oracles are referred to as oracular problems. Okay. And this is query complexity is easier to determine, or at least the bounds of the query complexity for a particular circuit is easier to determine as compared to the circuit complexity of a circuit. Since we don't really need to know the inner workings of this black box operator. So for example, we have here a query. The algorithm says, Oracle, does item one satisfy property X? So assume that we have a, let's say, a database that contains several elements. So the algorithm may ask the Oracle, Oracle, does item one satisfy property X? The Oracle may say, no. And so we can proceed to the next item. We can ask the Oracle again, Oracle, does item 2 satisfy property X? And the Oracle uh, may say yes if item 2 is the item that satisfies property X. So, kung paano niya ginawa yung satisfiability check, we don't really care about it. We just only care about the oracle's answer. Okay. Now there are so-called quantum oracles, and these oracles are actually just Boolean functions that maps binary strings into either 0 or 1. So when we ask the oracle, we provide it with a binary string here. Let's say a binary string composed of n bits or n qubits, and then the oracle responds to us by either a 0 or a 1. Okay. And so since quantum oracles are just basically Boolean functions, and so we can define these oracles as a truth table. So I think kanina may nai-present na si Sir Bob about truth tables implementation of some quantum gates. So same lang naman ito nun. And so we can implement it using logic gates. Okay, so again, emphasis on the logic because ito naman talaga yung nagpapatakbo ng computation, no? Programming is just a means for us to convey the logic, our logic to the computer, and then the computer will execute the logic for us. Okay, and then uh, we observe the transformation on the states. Doesn't matter if it's classical or quantum, but the same applies for both setting. Now, as Sir Bob has mentioned earlier, quantum oracles are required to be unitary operations. So just like other quantum gates, quantum operators, quantum oracles are also required to be unitary. And so this expression must be satisfied. Okay. So when we apply the oracle to a state and apply it again, we'll just receive its original state. Okay. So it must be reversible. And also, oracles are specific to the problem that we are solving. So, yung implementation ng oracle specific to the problem at hand is, again, hindi na natin concerned, but we assume that the oracle provides us with the correct answer. Okay. So, in the image in the right, no? So let's say initially we just have the input x, and then we ask the oracle, and then it provides us the input f of x. Okay, but since quantum oracles as quantum gates are required to be reversible, and so we can introduce another qubit, in this case the qubit y, and then apply an XOR operation to the output f of x and the state of y, qubit y, which will result to this expression, which is the XOR of y and the output f of x. Okay. Okay, so this is just an XOR gate or exclusive OR gate. Okay, so these are quantum oracles. Okay, so in the right, no? Again, ito yung illustration natin ng quantum oracle, which is a reversible implementation ng function ng oracle. Below is just the mas standard na representation ng quantum oracle in a quantum circuit. So, Sir Bob has mentioned din kanina, no, yung operator U sub F, which is, again, a standard notation for a unitary operator in quantum computing. So this is a unitary operator that implements the function f. Okay, so subscript yung f. So whatever the function is, it will be dependent on the problem that needs to be solved. Okay, and later makakita tayo ng, I think, 3 or 4 problems um, um, that are solved by a quantum processor. Okay, so yung nasa baba naman is just the um, transformation of the initial states 0, 0, and 1, 0 um, when applied with the unitary operator U sub f, which is our oracle. Okay. So again, so when we set y, the state y, to be in the state 0, then basically we are changing the state of the y qubit into the state corresponding to the answer of the oracle, which is f of x. So in this case, since this is f of 0, then 0 XOR f of 0 will just be f of 0. And the same goes for the output f of 1. So we'll have here f of 1. Okay. So this is just a generalization, yung y XOR f of x. Okay. But if we will consider the specific case wherein we set the state of the qubit y into the initial state 0, then we will get this output state. So effectively recording the output of the oracle into the qubit y. Okay. So don't worry, because I'll be providing the slides in a while. And so you can go through this material at a much slower pace. But I will just be discussing the contents of this presentation to you in a bit high level um, uh, in the interest of time. Okay. So if we have quantum oracles, we also have quantum phase oracles. So recall that in the operation of quantum oracle, we are basically recording the output of the oracle, which is f of x, into the state of the qubit y. But an alternative means of recording the output f of x of the oracle is by um, implementing or encoding the output f of x into the phase of the qubit x. So um, we can do so by instantiating the state of the qubit y into the ket negative state, which is this one. So if you will recall in Serba's presentation, we can arrive at the negative ket negative state by applying a Hadamard operation into the ket1 state. So this is the ket negative state. And then the operation of the quantum oracle on the answer and input qubits. So the answer qubit is the y qubit, while the input qubits is the x qubit. So the operation of the quantum oracle on the answer input qubits will be as such. Okay, so here we can effectively encode the answer of the oracle into the phase of the input qubit x instead of the answer qubit y. Okay. Um, so the input qubit acquires a phase of -1 raised to the output f of x. Okay. So this operation or the result of this operation um, is called a phase kickback because we are effectively changing the phase of the input qubit x by the uh, um, output of the oracle f of x. Okay, um, and such quantum oracles, are so-called quantum phase oracles because instead of directly recording or encoding the output of the oracle into the uh, answer qubit y, uh, the output f of x is encoded into the phase of the input qubit x. Okay. So quantum phase oracles are heavily used um, in the succeeding algorithms that I'll be discussing later. So just a very quick um, run through of the presentation of quantum algorithms in the literature. As Sir Bob has mentioned, eventually you will be needing to read books on quantum computing, papers on quantum computing, and you will be facing this illustration. So in the right, we have a circuit representation of a quantum algorithm, and or sorry, in the left, we have a circuit representation of a quantum algorithm, which is read from left to right. And on the right, we have a algorithm or enumerated steps representation of the algorithm. So both are just equivalent. Different representations lang sila. So kung babasahin natin yung circuit sa left, we can read it as the following step-by-step algorithm. Okay? So, uh, hindi na tayo magugulat kung makakita tayo nito sa mga papers. Okay? So, if we want to do research, or we want to do implementations of published quantum algorithms, then we need to be able to read these presentations of algorithms, quantum algorithms. And also, another representation is the walkthrough of the transformations of the initial state into the um, step-by-step states. Okay, so equivalent lang din itong nasa left and nasa right. So I think na-go through din ni Sir Bob kanina itong notation o yung ket notation na ginagamit sa quantum computing, and so we need to familiarize ourselves sa ganitong notation so that pag nakita natin, hindi tayo ma-disheartened, but instead um, we are equipped to read itong mga ganitong notation. So this is just a basically just a fancy notation for quantum computation. Okay? I think na-go through naman na ito doon sa mga previous presentations. And lastly, another equivalent representation is itong nasa right naman, which is the matrix vector sequence of operations. So itong nasa left is just below up lang natin dito sa right. And if we want to really understand how an algorithm or a quantum subroutine works, we need to be able to evaluate each step in the algorithm as a series of matrix of vector operations. And so that we can verify for ourselves the correctness of these algorithms also. Okay, so I highly encourage everyone to practice this kind of evaluation of quantum algorithms in pen and paper even after this lecture series para mas matutunan natin talaga kung paano ba siya gumagana. Okay, so moving on to some early quantum algorithms, let's begin. So first, we have the problem of identifying the parity of bits. Okay, so in this problem, we are given two bits, b sub 0 and b sub 1. And the parity of these bits is unknown, and we can define the parity of these bits as even parity or odd parity. So with even parity, the number of ones in the bits b sub 0 and b sub 1 is even. So uh, the parity is even, or the number of ones is even, is first if b sub 0 is equal to b sub 1, and they are both equal to 0. Okay, or both b sub 0 and b sub 1 has the value of 1. Okay, so dahil 2 yon, so even. Now for odd parity, this is the case wherein b sub 0 and b sub 1 are not equal. So either b sub 0 is 0 and b sub 1 is 1, or the other way around. And equivalently, we can define the parity of bits b sub 0 and b sub 1 by taking the XOR of these bits. So we can see in table 1 the evaluation of the XOR of bits B sub 0 and B sub 1. So makita natin if both are B sub 0 and B sub 1 has the same value like 0 and 0, then it is even parity. Or if they have both both they have the value of 1, then that's even parity also. But if isa lang yung 1, then that's odd parity. Okay, so this is the first problem. So we want to identify um, the parity of two unknown bits, B sub 0 and B sub 1. Okay, so for a classical algorithm that solves a parity problem, we can do the following. First, we query the classical oracle for the value of B sub 0 by inquiring about f of 0. So here, the input is the index of the bit. Okay, so we ask first the oracle, hey oracle, what is the value of b sub 0? And so the oracle replies with the output f of 0 equals to b sub 0. And we also do that for b sub 1. So in this case, in the classical case, the query complexity is 2 since we need to ask the oracle twice for us to be able to get to know the value of b sub 0 and b sub 1. And then after knowing the values of b sub 0 and b sub 1, we can then evaluate b sub 0 x or b sub 1. So if it is a 0, then the parity is even. But if it is a 1, then the parity is odd. Okay? So we have to ask the oracle twice for us to be able to answer the parity problem. So in this case, we just have we utilize since we are asking the oracle twice, then its query complexity is in O of 1 or ano naman, no, constant time naman. Okay? So we have 2 bits, then we need to ask twice the oracle for us to answer the problem. Now for the quantum algorithm naman, we have Deutsch algorithm. And surprisingly, we can ask the oracle just once for us to answer the parity problem. So this is how it goes. In the right side, we see the circuit implementation of Deutsch algorithm. So it is very simple. And nakita na rin natin kanina, no? This is a parang ano siya, ano ba, boilerplate quantum circuit since we are just using Hadamard gates, the oracle gate or operator u sub f, and then a measure gate. Okay? So yung top qubit is the answer qubit prepared in state ket negative, and then the second qubit is second qubit or the input qubit is prepared in ket 0, no, which provides us with the uh, answer to the parity problem. So recall that what we are using here is a quantum phase oracle kasi we prepared the answer qubit into the ket negative na state. Okay? So very simple lang siya yung Deutsch algorithm. And you can code it easily doon sa IBM Quantum. Okay? So for us to be able to prepare the answer qubit into the ket negative state, we apply an X operator to qubit q sub 0. Then we apply an Hadamard operator to the qubit q sub 0. So we will arrive into the ket negative state. And then we apply a Hadamard operator into the qubit q sub 1. So itong 0 state ay malalagay sa superposition ng 0 and 1. Okay? And then we apply the 2 qubit u sub f operator or the oracle to qubits q sub 0 and q sub 1. Basically, or effectively, um, querying the oracle kung ano ba yung values for b sub 0 and b sub 1. So, imagine no, na yung magiging superposition state ng qubit q sub 1 will be a superposition of 0 and 1. And so that these states corresponds to the indices 0 and 1 na kung saan magbibigay si Oracle ng answer. Okay? So again, if the resulting answer is 0, then the parity is even, else the parity is odd. And we have query complexity of 1 because we just need to ask the Oracle once to answer the parity problem in the quantum setting using Deutsch algorithm. So I think we have a walkthrough in the next slide. Okay. So um, doon sa ano 'no, dito sa step na 'to, I think doon sa algorithm, it's step 5, mag-arrive tayo sa ganitong state. You can walk through the computation nung circuit ng Deutsch algorithm offline, but we will arrive in this state. So notice na itong -1 raised to f of 0 and -1 raised to f of 1 is basically um, a phase kickback subroutine because we are encoding the output f of 0 and f of 1 doon sa phase noong states ket 0 and ket 1 noong input qubit natin. Okay? So this is an implementation of the phase kickback subroutine. And then here, after nung pag-apply natin ng Hadamard operation sa state na ito, um, we can simplify yung state with this expression. No? So yung 0, ket 0, will be transformed into this state, and then yung state ket 1 will be transformed into this state. And so, when we measure itong state nitong input qubit natin, if we get a 0, then it only means that the parity is even because b sub 0 is equal to b sub 1. But if you will get a state or classical value of 1, then it only means that b sub 0 is not equal to b sub 1, and so the parity is even. Okay, so here on the right side is just a enumerated observations into the um, inner workings of the Deutsch algorithm. So you can go through this step by step and verify on your end offline how Deutsch algorithm performs given the set of initial quantum states. Okay. Okay, so as an illustration, so we ask the oracle, so this is the state of the input qubit in a superposition of the states ket 0 and ket 1. And then we ask the oracle um, for its answer given this input. And then the oracle provides us with its answer, which is a superposition of the states ket 0 and ket 1 with the phase kickback for the outputs f of 0 and f of 1. So with just one query to the oracle, we were able to answer the parity problem in one query. Okay, so this is just another illustration of the Deutsch algorithm. So we provide it with the indices 0 and 1, and then it provides us with the XOR of B sub 0 and B sub 1. Again, in the state of the input qubit, Q sub 1. So we can also scale this no, to more than 1 qubits with n greater than 2. What we can do is to ask the oracle about the parity of pairs of indices. So, for example, pairs of indices 0 and 1, pair 2 and 3, pair 4 and 5, and so on, up to n minus 2, comma n minus 1. And so doing that will require us n over 2 queries. So sa classical setting, we need to query the oracle n times for n bits, while sa quantum setting, we need to query the oracle n over 2 times. But yung query complexity nun will still be in O of n. Okay? So that will be linear. So in this case, kung titingnan natin yung query complexity, yung asymptotic, no? Pareho lang siya. Pero sa quantum setting, we just need to query the oracle half of the time as compared to the classical algorithm. Okay? So again, you can work out yung ano no, yung transformation ng mga states offline once you get a copy of the slides. Okay. So this is just again another illustration wherein ito mga indices doon sa binary strings of length n. So here is pair 0, 1, and then we will receive the answer of the oracle for b sub 0, x or b sub 1, and then for pair input pair indices 2, 3, we will have the answer of the oracle for b sub 2, x or b sub 3, and so on. So this will be n over 2 queries to the oracle. Okay, so that's the first problem, the parity problem. And we see na doon sa query complexity, no, kung asymptotic ang titignan, linear lang din, no? Same with the classical. Pero yung in actuality, we just need to query the oracle half of the number of the queries in the classical setting. Okay? So if that's, let's say, 1 million, they'll just need to query the oracle 500,000 times instead of 1 million queries. Okay, so moving on to problem number 2, which is the constant or balanced function. So again, we are given a function that is a mapping of n-bit binary strings into either 0 or 1. Okay, and the premise is that f is either constant or balanced function. So a graphical representation of that is um, the tables A, B, and C. So sa table A, we see that function f of x is a constant function such that whatever 2-bit binary string we provide it, it will just give us an output of 0. So it is a constant function um, that returns 0 all the time. And then in table B, the function f of x is also constant, but in this case, it returns a value of 1 for all the input n-bit binary strings. Okay, so yung function f of x sa case A and case B are just constant functions that return 0 and 1 respectively. Now for the function f of x in table C, we see that it is a balanced function since half of the time it gives us an output of 0 and half of the time it gives us an output of 1. Okay? So ito, hati talaga yung binibigay niya na output sa 0 and 1 doon sa mga input n-bit binary string. So function f of x in table C is a balanced function, while function f of x in tables A and B are constant functions. So the question is, given a function f, is f constant or a balanced function? So let's see how we can solve that problem. So for the classical algorithm, we can have 3 cases. So the first is, again, we might get all zeros as output. So this is a constant function. In case 2, case 1.2, we might get all ones as output. So again, this is a constant function. In case 1.3, we might get a mix of zeros and ones as output. So, and then half, so this is a balanced function. Okay. So in the classical setting, we need to evaluate function f on half of all the possible inputs n-bit binary string. Why half? Kasi by querying the oracle, half of the total number of bit strings and bit binary strings, we can know whether the function f falls under case 1.1, case 1.2, or case 1.3. Okay. We need, and then for case 1.1, if we get a 0, then f is a constant function. And if we get a 1 for half of the queries, then we get a um, balance function. Okay. And then for case 1.2, if we get a 0, then f is a balance function um, for the remaining half of the bit strings. And then if we get a 1, then f is a constant function. Okay, so imagine if we have 10 binary strings, and then we query the oracle 5 times, so, and then we get a 0. And so we might guess na, ano to, it could be a constant function wherein all outputs are 0, or a balanced function wherein the remaining 5 evaluations are ones, no? But if we ask the oracle again 1 time, and then we get a 0, then we can conclude that function f is a constant function that returns 0 all the time. But if we get a 1, then we can conclude that function f is a balanced function. No? Kasi based on the promise that was given to us, we know that the remaining 4 outputs will be all ones. Okay. And note that there is no need for one more evaluation in the case 1.3, since by the promise, we know that f is a balanced function. Okay. And so the count of all the binary n-bit binary strings is 2 to the n, and half of this is 2 to the n minus 1. So that would be 2 to the n over 2. So with the classical algorithm, the query complexity is 2 to the n minus 1 plus 1, since we need to query the oracle one more time, no, to be sure if the function f is a constant or balanced function. And this is in O of 2 to the n, which is exponential with respect to the number of qubits in the circuit. Now we proceed to the quantum setting, and we have the Deutsch-Josa algorithm that solves the same problem. Okay, and we see that the circuit in the right is just a generalization of the circuit for the Deutsch algorithm. So pinadami lang natin yung input qubits. Instead of 1, so, ginawa na natin siyang n, because we need n qubits to encode the 2 to the n n-bit binary strings. Okay, and then what we can so now again, going through the same series of quantum operations, and then measuring the output state of the qubits q sub 1 to q sub n into classical bits c sub 1 to c sub n. And then if we get a 0, um, just like in the Deutsch algorithm, then we can conclude that the function f is a constant function. Else, the function f is a balanced function. So with this quantum algorithm, with the Deutsch-Josa algorithm, you can say that the query complexity is just 1. So regardless kung gaano karami pa yung number ng n-bit binary strings that we will need to evaluate just to answer the question of whether the function f is constant or balanced. So why is that so? So tingnan natin. Okay, so here is just a very brief walkthrough of the Deutsch-Josa algorithm. No? So in this step of the algorithm, we will arrive at this particular state of the qubit states, input qubit states. And we see that meron na namang phase kickback na subroutine na nag-take effect, wherein the output of the oracle, which is f of x, for each x in the set of n-bit binary strings, is encoded into the phase of each superposition quantum state. So again, as mentioned by Sir Bob, di ba? Pag nakakita tayo ng ganito, this is a linear superposition of quantum states. And we denote each superposition quantum state as the state ket z, such that z is a binary encoding of the decimal numbers 0 to n minus 1. Okay? So here, nalalaman natin yung yung sagot ni Oracle sa bawat uh, index, no? So let's say f of 0, then malalaman natin kung ang sagot ba niya ay 0 or 1. Okay? And yun. So naka-encode ngayon doon sa face noong mga states natin yung sagot ng Oracle. And you can go through this series of observations um, offline, and you can verify that if the function f is constant, then we are sure to get the bit string 0 upon measurement. Okay? But if we will get um, a classical output other than the bit string zeros, or these are n zeros, then we are sure to get a bit string. Then we are sure that the function f is balanced. Okay? So, andito sa uh, by following observations 1, 2, and 3, we will arrive at this conclusion. So observation 4. So you can verify um, this offline. Okay. So ito, this is a illustration of the of how the JOS algorithm works. So sabay-sabay natin na no na pinaprovide sa Oracle yung binary encoding ng lahat ng indices um, uh, from 0 to n minus 1. And then ang response niya is an encoding of the answer to whether function f is a balanced or constant function. Okay, so yung ma-receive natin is a string, binary string x, which is one of the binary strings in the 2 to the n possible binary strings in this set, n bit binary strings. Okay. So that's it for the um, balance or constant function problem. Now, in the interest of time, let me skip problem 3. You can go through this on your own time, but let me proceed to a more important algorithm, which is Grover's algorithm. So this is one of the quantum algorithms that has shown an oracle separation, no, between classical and quantum setting. Oracle separation meaning merong notable difference so sa query complexity sa classical setting and quantum setting. Okay, so in this problem, we are searching through an unstructured database for an item. Okay, and this item and for this item, the function f of x returns an output of 1. So we want to know what is this, what is the index of this item in the unstructured database. Okay. And again, we will be using an oracle implemented as the operator u sub f in the quantum circuit. Um, and an example of this unstructured database problem is this one. So imagine we have a phone book, no? This is a classic example. So if we want to search for the number of Dave, since this is alphabetically ordered, we can just look directly into Dave's entry, and then we would know that his number is 8854187. But if we will reverse the problem such that given a phone number, we want to know who is the person that owns that number, that unique phone number, then it will be quite difficult, no? And so um, we need to um, introduce some new quantum operations that were not yet introduced before, um, which is used in Grover's algorithm. Okay, so in the classical setting, if we are lucky, So suppose the database contains n elements and we are lucky, and in our first try, we immediately found the item that we are looking for. And so we just have one, um, in this case, we had just had one try and then we found the solution. But if we are so unlucky, such that we were able to find the element that we are looking for in our last try, then that would be n queries to the oracle. But in average, we will need n plus 1 over 2 queries to the oracle for us to be able to find the element that we are looking for. So here is an evaluation of this expression, and you can verify it for yourself offline. So this is just a simple arithmetic sequence. And the total or the average number of queries will be n plus 1 over 2. So the average query complexity in the classical setting will be in O of n, okay, um, um, which is exponential if we will um, use lower n number of qubits, such that um, lowercase n corresponds to log base 2 of the capital N. Okay, I think I defined it here somewhere. Okay, so here. So this is Grover's algorithm, and we will be using n plus 1 qubits, q sub 0 to q sub n, and then we prepare it in initial state 0. So where lowercase n is the log base 2 of the capital N, uppercase N. Okay, so because we just need this much of qubits to represent this much entries in the database. So again, the qubit q sub 0 is the answer qubit, while qubits q sub 1 to q sub n are the input qubits. So we can so again, following the same routine as in the previous algorithms, we put into a superposition um, qubits q sub 0 to q sub n. And then for this number of iterations, we apply the query to the oracle, which is denoted as V, operator V. And then we apply an n qubit operator W to qubits q sub 1 to q sub n. So, andito yung magic sauce ng Grover's algorithm. Dito sa application ng query to the oracle, u sub f, denoted as V, and the application of the operator W to the resulting qubit. So, let us see a brief walkthrough. Okay, so we can represent the state that we are looking for as the state ket A, and then the rest of the other superposition quantum states as perpendicular to the state ket A, denoted by the state A subperpendicular. Okay, so Grover's algorithm works by rotating the initial state. So the initial state in this case is the state phi. So through the iterative application of the unitary operator U sub f, which is the oracle, and the um, rotation operator W, we are able to bring closer the initial state ket phi into the desired state ket A by 2 times theta angles for every iteration. Okay, so the goal is to bring this state, initial state ket phi, closer to the desired state ket A by this iterative application of operators phi and W. Okay, so ano lang ito, no? Mirror operation or reflection operation along these perpendicular states, A subperpendicular and phi subperpendicular. So through this iterative operation, nailalapit natin yung state ng system natin into the desired state ket A. Okay, so this is just a further elaboration on how operators V and W works. Okay, so you can again verify this offline. So I'll just skip some of the slides in the interest of time, so that the next presenter will still have time to discuss. So okay, so in summary, so we have these, I don't know, learning objectives. First is to identify and explain in high level the inner workings of some early quantum algorithms, and we have gone through Deutsch algorithm for the parity problem, Deutsch-Joseph algorithm for the constant or balance function problem. We skipped the Bernstein-Basirani's algorithm for the secret string problem, but this is just again a generalization of the Deutsch algorithm. And then same circuit lang din, no? Naiiba lang yung oracle, since iba yung problem. And then we've gone through Grover's algorithm in a very high level fashion, for the unstructured search problem. Okay. I hope you can go through the materials again offline after the lecture. And then second, explain how these early quantum algorithms are advantageous over their counterpart classical algorithms. So I hope you can go through the graphical illustrations on how these quantum algorithms differ from their classical counterparts, and then ano ba yung difference nila. So basically, as Sir Babas mentioned earlier, yung quantum superposition talaga is what uh, provides quantum algorithms the advantage. No, kasi the oracle can evaluate each quantum state, no, ng sabay-sabay, kasi nasa superposition sila. Instead of sa classical setting, no, parang isa-isa natin na tinatanong sa oracle yung evaluation niya doon sa bawat state. And for the third objective, identify and explain key subroutines in these early quantum algorithms. So yung first is yung superposition of states. So this is a very key subroutine that provides quantum algorithms is advantage over their classical counterparts. Second is yung phase kickback in quantum phase oracles. So with the phase kickback subroutine, na i-encode natin dun sa phase noong states, input qubit states, yung sagot ng oracle, which are the evaluations of x. So ito yung mga f of x. Okay. And then third would be amplitude amplification, rotation about a state. So ito naman yung sa Grover's algorithm, no, yung minention ko kanina, itong mga rotations. So these are amplitude amplification kasi ini-increase natin yung amplitude nitong target state A, and then nire-reduce natin yung amplitude nitong perpendicular state A subperpendicular. Okay, so habang lumalapit yung state ng system natin dito sa state A, uh, ang meaning nun is that lumalaki ng lumalaki itong amplitude nitong target state A natin, such that kapag nag-measure tayo ng state ng system, with very high probability, we will get as classical value the state A, which is yung hinahanap natin na index doon sa database. Okay. So again, we have these three key subroutines. So for exercise other resources, I'll be providing them offline through JBest, no, doon sa Discord, or I think sa Google Classroom. And then for the references, so you can search the net for copies of these references. Coincidentally, no, yung authors ito ay both Wong, yung family name, si Thomas Wong and si Hugh Yung Wong, and these are very good references on the algorithms. And so dito kay Hugh Yung Wong, meron din siya nung implementation sa IBM Quantum. Dito kay Thomas Wong, more of ano lang, theory. Now, just a reminder, as Brian Greene has said, eat your frog, meaning don't skip the hard parts. So don't skip the math, and the rest will be easy peasy. Kasi yung programming part nito, as Sir Bob has mentioned, madali lang talaga. Ang hard part or difficult part is understanding the mathematics and verifying that a circuit does what it does. No? So thank you. That's all for my presentation. And if you want to connect with me, you can send me an email through this email address. So thank you.
Awesome, awesome. Ayan, thank you for Sir Jeff for that very insightful and
Thank
wonderful
you, Jeff.
presentation. Yes, so hindi na ako magre-recap kasi Sir Jeff has already gave us a summary of what we've done for today, for tonight. Yeah, well, just a sec. Let me share my screen. Ayan. Okay. All right. Yeah. Sorry for the 10-minute extension. So yeah, again, may we request everyone to please turn on your cameras. Nag-share pa naman ako and mag-unshare ulit. Pero yeah, hello. If you can, please turn on your cameras so that we can see you. Ayan. So yes, yes. Ayan, we're very excited, no, while we're preparing for the hackathon, no. So hopefully we'll see some of you face to face, no, kapag nandoon na. Oh, yeah. All right. All right. Sige, let's wait for the others. And so if you can't turn on your cam, it's okay. No, mag-react na lang kayo with the heart or a haha para ano, your presence is still uh yeah, heard. Ayan. So, all right. Sige. Uh yes, Sir Elmer.
Okay, on the count of three. Wait, wait. Okay, 1, 2, smile. Okay, the next frame. 1, 2, smile. Next frame. 1, 2, smile. Okay, I will not count on the last frame because none of you are opening your cameras naman. So, i-screenshot ko pa rin siya. Yeah, best. Thank you.
Awesome, awesome. Thank you po, sir. Thank you, guys. Okay. All right. At this point, yeah, let me just prepare. Okay, at this point, we would like everyone to fill this form up now for your attendance. Okay. All right. Okay. So after you filled that attendance form, yeah, you're free to leave the call na. Thank you everyone for staying with us until 7:42. So we started since 5 p.m. and okay. Ayan, Sir Jeff said that he might provide a video recording for a more complete presentation. Ayan, sige. Thank you very much for Sir Jeff. And also guys, we'll be sending the supplementary notebooks tomorrow na lang since I'm doing it on my Jupyter notebook and then nung nilipat ko siya sa Colab, hindi na siya nagwo-work. So let me just see what we can do and troubleshoot it and even convert it into an IBM quantum experience. Yeah. But yeah, the homework will be posted tomorrow as well, together with the supplementary notebook. So yeah, please take a rest. Ayan, so let the concepts and theories settle in. And yeah, we will see you next week. Okay? Thank you everyone. Lab day tayo next week. Bye-bye.
Thank you. Bye.
Thank you. Happy weekend.